I will begin. With a word of prayer. Heavenly Father, we thank you for this day. I thank you for the students, and just pray that you'd guide my steps, help me to understand what it is we're covering, and to help to make some more sense out of just the concept of Hilbert space and orthonormal basis and all this, Lord. In the name of my prayer, Jesus, amen. All right, so here we go. Let me remind you guys. Definition. Oof. No, you don't. No, you don't. Thanks, Jacob. It went off the rim of the trash can and went out into the hallway. That's why I was laughing. So orthonormal basis is what I'm defining. All right. An orthonormal system B in an inner product space is called an orthonormal basis. If each X in E has unique representation X equals to the sum n equals 1 to infinity of alpha n xn, where alpha n are elements of the complex numbers and xn are distinct elements of B. All right. Now, we ended on the note that a complete orthonormal sequence is an orthonormal basis. What was a complete? What was meant by complete orthonormal sequence? That was on the page before. To say it's complete is to say that complete is to say every x can be written like this, right? So the ability to write x equals to the summation of the inner product of x with xn times xn from n equals 1 to infinity. If you can do that for every x in the space, then the orthonormal sequence xn is said to be complete. So this is completeness for an orthonormal sequence. Now I suppose so the thing I'm wondering about, guys, is an orthonormal system, cardinality here, you know? Right? We're not, I don't think that this definition is necessarily forcing the orthonormal system to be countably infinite, you know? Or even countable. Like we're extending the notion of linear combination to this, you know, to infinite series, right? So we're taking countable linear combinations, but I think it's, at least at principle right now, possible that the orthonormal system B could be like, you know, beyond countably infinite, right? Like, you know, as large as the, yeah, it could be uncountable. Now, that may or may not be something this book ever gets to, but it seems like that's something you could think about, right? Okay, so next up here, move along. Where was I? He says, if you have a complete orthonormal sequence, inner product space, then the set, this is a claim, if xn is complete orthonormal sequence in inner product space E, then span of x1, x2, dot, 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 dot. Okay, so we're talking, he's defining the span of the sequence, right, to be, what is it? It is equal to, parentheses, the sum k equals 1 to n of alpha k xk such that n is a natural number and alpha 1 through alpha k are complex numbers. Aha! So, no, he claims, I don't know if I wrote the punchline or not. I didn't write the punchline out. Then this is dense in E. Why is that true? What does that mean?
How do we know that's the closure of the set then?
Yeah, well, I mean, dense would mean, yeah, that the closure of the span is all of E again. That's true. But let's see. So just to, first of all, if it's a complete orthonormal sequence, by what we talked about at the end of last class, it's a basis, right? It's a basis.
Yeah.
So what was one characterization of the completion? I don't think, he doesn't have any like words around this. He just states it. He doesn't even say it's easy. So I think this is an immediately obvious thing if you just put the words together and think through it, is my point. Do you remember this? The complete, one of the ways we could define the completion is by putting in all the limits of, the limit points of all convergent sequences, isn't that right?
Yeah.
Or is it Cauchy? I'm trying to remember what was the, there was a sequential definition of completion that we had before that I have, you guys should know. What's that?
I remember that in topology.
No, not the topological definition. I want the sequential definition of completeness here.
We're talking about completeness or closure, or the set.
Well, closure, yeah, sure, the closure.
Yeah.
I mean, the sequential definition of closure would also suffice.
Page 16.
Page 16. The intersection of, well, yes, the intersection of all closed sets containing S, that's lovely, but that's not what I want. Maybe theorem 1.3.23. The closure of the set S is the set of all limits of all convergent sequences of elements of S. So closure of S is X and E such that there exists, yeah, that's what we want. So this theorem, this is what I'm after, guys. And so this is the other danger of my review sheet, is I haven't included this maybe. See, the one thing that's missing from my review sheet for you guys is theorems that you should know, but I don't expect you to be able to prove. That's another category of your studying you shouldn't neglect, right? Because these theorems are lifeblood, right? This says the closure of S is equal to X in E, right? Such that there exists all right, such that there exists, x1, x2, dot, 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 in S, such that x I goes to x, I believe. Or xn, n, fine, n. Ni, whatever. Anyway, the sequence. So it is literally all limit points of convergent sequences of S. This is the closure, right? So why would the closure of this span be all of E?
Because we can take like this, the weights, because the inner product can give us any element of the span. And what I guess it's
Like, yeah, I guess, so suppose that you, let's see here. I mean, what I was thinking roughly is that these are the partial sums of these series. And so convergence of the partial sums is essentially built into the theorem. I'm being a little bit fuzzy.
Yeah, I mean, this is the topological definition. We just never got to it either. I mean, like, this is one way you can define it. Like, your set, if you have a point and you want to say, is it closed? You say, does all possible sequences of numbers that limit to this point exist in that set? So, like, you know, the closure can also be thought of as like the set that contained all possible sequences that limit to that point.
Yeah, but the closure is not the set of sequences. It's the set of, like, the limit points, right?
Yes.
Yeah.
Yeah, it has to contain all those limit points, yeah.
So, oh, okay,
So if you take like any partial sum of the sequence, that partial sum has to be in the set again.
okay, so, like, let's see here. So let me be specific here. So
well, the limit of partial sums has to be in the set, right?
right, let x be an element of E, right?
Mm-hmm.
Then x is equal to the sum, right? N equals 1 to infinity
Yeah.
of this right here, right? By I mean, this is, if we have a complete orthonormal sequence, this is by definition, right? But this is literally the limit as n goes to infinity, right? Of the sum, k equals 1 to n, of x with xk, xk. And this is an element of the span of the sequence. So we're looking, so that is then by theorem 1.3.23 necessarily in the closure of S. But x is arbitrary, so that definitely proves that. So that's an element of the closure of the span of xk. So I think that would that we've proved what? E is a subset of the span. Well, the closure of the span, right? And then the other direction is because E is a vector space. Yeah. So spans are subspaces, yeah. Okay, so anyway, got that on my system. So that is why he doesn't explain, because it is, can be, yeah, trivial. Trivial still takes me 5 minutes, but anyway. Let's see here. So theorem 3.4.14, an orthonormal sequence xn in Hilbert space H is complete if and only if the inner product of x with xn equal to 0 for all n in n implies x equal to 0. So completeness of the sequence is essentially equivalent to non-degeneracy in some sense of the inner product with respect to the sequence. I need to get myself like a paperweight or something. Actually, I need to take the time to scan this stupid book so I can stop carrying it around like a dummy. Usually I scan it and print it out, so I've got a piece of paper. I've gotten lazy. I've been holding the book instead, which means I'm slowly but surely filling this book full of eraser dust, which is sad. Because unlike chalk, this kind of eraser dust, like you can't get off the page, you know? It's like, anyway. All right, so this is the theorem. Let's see here. So how's the proof go? All right, so if we assume, I'll assume completeness, right? Then x is equal to the sum, right, of the inner product of x with, let's say, xj, sum over j. If x with xn is equal to 0 for all n in n, then what do we get? We have, I'm going to plug it in. I'm just going to skip a step if you guys don't mind. We get that the sum j equals 1 to infinity, right, of the inner product of x with xj times xj with xn is equal to 0. Oh, wait a minute, no, I'm being dumb. It's easier than this. Flag on the play, making it too hard, way easier. What do I need to write down? Excuse me for using some sort of football lingo in here. Oh, what's wrong with me? Okay. It's like right in front of us, yeah? So we have this, right? We're assuming this for all n, so thus x is equal to the sum j equals 1 to infinity of 0 times xj, which is 0. All right, great. So there you go. There's the forward implication. That wasn't hard. Surely the reverse implication is going to cause me some heartburn or something, right? Let's see here. The other direction. So let's suppose, x with xn equal to 0 for all n and n implies x equal to 0. We'd like to show that implies completeness. We want to show that is a sufficient condition to get completeness of the orthonormal sequence, right? So we are presupposing orthonormality of the sequence, right? So I'm assuming we already have that, you know, xi with xj is Kronecker delta ij, right? So what does it take to show it's complete?
Did you go to the other board?
Yeah, sorry, Audric. Is that, can you see it?
Yes. Yeah, I can see it.
All right, so I'm trying to go the other way. Trying to prove that this orthonormal sequence is complete. Unless I've misread this and I'm supposed to prove that it's orthonormal.
No, an orthonormal
Oh.
sequence that's within the
Okay, so the orthonormality is as a presupposition. All right.
So I guess we take an arbitrary element x and we have to show that to be expressed as
Ah, okay. I think he uses y. So let y be an element of the Hilbert space, right? And consider, you know, z equals to the sum j equals 1 to infinity of z with, my bad, y with xj. All right, so let's calculate. I'm going to calculate the inner product of y minus z with xn. All right? And so to do such is to calculate the inner product of the sum j equals 1 to infinity of y xj, oh my bad, that was the z. I'm a bit of minus here, plus y. Sorry about that. My bad. But then by additivity, we got, let's see here. So I have minus the sum, j equals 1 to infinity, right, of y with xj times the inner product of xj with xn, and then plus the inner product of y with xn. Now, that is one of my favorite things, the Kronecker delta, the natural enemy of the finite sum. So the finite sum dies, and in the blood mist that was it, we're left with replacing the index j with the index n. N after here is fixed. J is the summation index, right? So we keep the n, get rid of the j, and we get minus y xn, xn, plus y xn. But of course xn is by the normality 1. And so what we have is 0. So therefore, y minus z is equal to 0, which tells me that y equals to z, and we're done. Because y equals to z proves that an arbitrary element of the Hilbert space can be written as the inner product expansion of itself. Yep. All right. Now, next, he says the formula in the following theorem, known as Parseval's formula, Marc Antoni Parseval de Chenis, I'm saying that wrong, I'm sure, 1755 to 1836. He said it can be interpreted as an extension of the Pythagorean formula to infinite sums. So, oh, funky. Look at this. Look at this one here. I'll move you back over here in a second, Audric.
Okay.
I'm just erasing. You're not missing anything. Oh, thank you. I'm glad you're keeping track of that, because I'm definitely not. So this is an orthonormal sequence in a Hilbert space. Orthonormal sequence in a Hilbert space, H is complete if and only if is complete if and only if Parseval's formula holds, which is that the length, the norm squared of x, is equal to the sum, n equals 1 to infinity, of the, yes, the absolute value of the inner product with x with xn squared. So this is going to largely rely on, the proof of this rests on that formula we derived last time, right? So the formula we proved last time, which was really straightforward, right? What's that? Yeah, Bessel's, well, I guess this is Bessel's equality. Namely this, the norm of x minus the summation k equals 1 to n of the inner product of x with xk in the xk direction. That norm squared is equal to the norm of x squared minus the sum k equals 1 to n of the absolute value of x minus x with xk, inner product of x with xk squared, right? Oh gosh, yeah, it's just obvious almost. Now that I write that, well, duh, right? Well, duh. So check it out, right? So the forward implication. Suppose you have completeness. What does that mean?
Completeness, and what we just defined.
Yeah,
Right.
in a Hilbert space, so complete as in it can be expressed as.
X is equal to, right? The sum, let's say n equals 1 to infinity of the inner product of x with xn, right?
Yeah, so we mean completeness that's by x can be represented by the inner product of the sequence with itself times the sequence.
Mm-hmm. So what happens here when I take the limit as n goes to infinity of this formula?
It becomes x.
Oh, 0.
So it's 0, yeah.
Yeah. And okay, so by continuity of the norm squared, I can pass the limit inside the norm, right? So we have those, we have proved that.
Right, because of it going to 0?
No, I mean the norm is continuous, and so the square of the norm is a continuous map as well. And if we have a continuous map, we can bring the limit inside a continuous function, right? Of course, you could work through the epsilonics here just the same if you really wanted to, but let me just operate at a slightly formal level here. I think that's fine. Thinking the limit as n goes to infinity, right? Let me call this equation star. Star yields 0 is equal to the norm of x squared minus the series n equals 1 to infinity of, absolute value of x with xn squared. And that is exactly the claim of Parseval's formula, right? Now, how about the other direction? So the other direction, I have what? I have the limit as n goes to infinity, right? Of what? Of the norm, let's see here. The norm of x squared minus the sum k equals 1 to n of this guy is equal to 0. I think if I'm careful in my application of Bessel's inequality here, we can prove that the limit of this has to be 0. And that the limit of this has to be 0, and if you can prove the limit of this has to be 0, that is, I believe, the same as saying that x is equal to that in the limit, which is the completeness. But I guess I would start. I'm saying I would, if I have this series, if I have this equality, right? That means that you have this limit among other things. I mean, technically, it means that the limit of. I mean, I can bring the limit to the other side, right? I mean, directly, I was hoping that would be, I mean, technically, it's this that I have, right? I mean, at the start, anyway. I mean, you can derive various things from this, but this is what's true, right? And then what was Parseval's inequality? Bessel's inequality. What was it? It was the
summation k plus 1 to n of the absolute value of the inner product of x comma xk quantity squared. So that's not necessary, yeah. It's necessary to the norm of x squared.
We know that. Maybe just, how about this? If I have the norm of x minus the sum, right? K equals 1 to n of the inner product of x with xk, right? That is less than or equal to, by the triangle inequality, the norm of x plus the, the norm of the sum. I wonder if this can get it for me. I'm just trying something, guys. It may or may not work, okay? I could look at the book and, see how to do it, but forgive me, I'm playing for a minute. I guess on the I guess that doesn't help much.
We have to get rid of that.
Yeah, that didn't help me. That didn't help me. Oh well. Ah. Sorry, I tried. I still feel like that's relevant, but here, let me turn the page here, find out what's waiting for us. Oh, well, he did write at the top of page 116 what I had written. That's a good sign. Therefore, grief. Well, okay, fine. He says what I had written before implies what we want. Huh. Sorry, I'm probably just being dumb at the moment. It's probably just obvious. So we're assuming that. Why does this imply? Yeah. Why does this imply that x is equal to? Why does this imply that the? I mean, he's claiming that that implies that the norm, right, of x minus the sum, k equals 1 to n, right? Well, more than that, he's claiming it implies that this is. Sorry, I'll get out of the way here in a second. I believe he's saying that that implies this is equal to 0. Excuse me. I mean, he does write.
Well, I guess it's,
Well,
go
he's
ahead.
saying that the norm of x minus the sum squared is equal to 0. I was thinking that, like, if you interchange limits, or if you limit inside.
Sorry, Audrey. There is an equation that he wrote down that I haven't written down yet. Maybe that's the key. Yeah. I think we did this last time, but I'll do it again. All right, so he's got his equation 3.32. Yeah. The norm of x minus, what is that? The sum k equals 1 to n of x with xk, that squared is equal to, he says.
Yeah, this is exactly what we needed, actually.
The norm of x squared minus the sum k equals 1 to n of the absolute value of x with xk squared.
So, if the left-hand side,
Oh,
yeah, the limit of the left-hand side is equal to 0.
right. Yeah, I mean, because I actually had written this before I erased it down here, and I pointed out that the limit of that is 0.
Yeah, so that means you can just add the sum on the other side, meaning that you get that the norm of x squared equal to the sum, and then I think that implies completeness because you can can write any x as its sum of inner products with itself.
Wait a minute. I already knew that.
Yeah.
Oh, the other way around. I'm a dummy. It's not that. This is. I'm stupid. I'm sorry, guys. This is dummy. I'm going backwards. This, we're in the case we're in right now, we have these are equal. Right? These are equal. Therefore, this goes to 0. But this going to 0 is tantamount to saying that if this norm squared goes to 0, then this goes to 0, right? As n goes to infinity. But that
Square root of that norm goes to the square root of the whole thing is 0. So therefore x goes to the sum, which is complete. Okay.
that means that x is equal to. That implies then that x is equal to that series. Yeah.
So it's basically just using Bessel's equality and then like looking at from starting one direction to the other.
Yeah. It's just all Bessel's equality, right? Yeah. Sorry, I have spent entirely too much time on that. Where are we? Right. So, okay, but anyway, so it's complete if and only if the norm squared is given by the sum of the coefficients, the moduli of the coefficients squared, right? And to calculate, so if we think of this as a basis, right? The coefficients of the basis are also given by the inner product, right? That's very nice. And then I think at this point, he starts rattling off examples. All right, so I will do the same, if that's okay with you guys. I'll try to be brief on the examples today because I have a habit of making examples spin into longer discussions than they need to be. All right, so the orthonormal system. And yes, I need to move you, Audric. 3.4.16. So he's got orthonormal system phi n of x is equal to e to the I n x divided by the square root of 2 pi. And this is for n in the integers. He says this is complete in L2. That's a little bit foreboding. He says proof of the completeness is not trivial. It'll be discussed in section. There's a section to discuss the completeness of this, all right? So next section. And then he says what? A simple change of scale allows us to represent a function in the form. So now for a sneaky trick, I believe, is what he's starting to get into. So this is the thing. When you study Fourier series, there's all kinds of like. People look at that Fourier half series and the full series, and there's all these different kind of sneaky tricks to go from one to the other, and if you do it right, you can steal work from one scenario to another, things like that. I think this is part of that story. All right, so he says, if we have a function f in L2, 0a, then He says a simple change of scale, you can write f of x as beta sub n times e to the 2n pi ix over a. Two n pi ix over a, yes. And the beta n will be given by 1 over a integral 1 over a integral from 0 to a f of t e to the minus 2n pi it over a. dt. Well, this is a really annoying thing to write in the middle of a section without any kind of like explanation or anything. Just, I mean, what you talking about, man? What? So if I'm to believe, let's see here. Change of scale, you say? See, if it was like, the thing that's bugging me, if it was sort of like minus a to a, I'd be more inclined to try to see the exact, I'm assuming that there's a connection between what's written in black and what's written in blue, yeah? That's the impression which is given here. And I don't want to believe it. Let's see here. Oh, goodness gracious.
This may be beyond me, but does this have to do with like the Fourier transform and inverse Fourier transform? Because I see an e to the negative, but on one side and e to the positive.
Does it have something to do with the Fourier transform? I mean, I think, yeah, sure. I think all of these things, in some sense, have something to do with the Fourier transform. But here, I think we're just talking about like a change of variables.
If it makes you feel better, it's literally the first thing they go over 3.5.
Oh, this?
Yeah.
So this is in 3.5.
Like it's the first thing in 3.5.
All right.
Oh, yeah, right.
But he does minus pi to pi. Well, but I don't see the 0 to a thing in here, Audric. I see minus pi to pi. See, that's what's like a minus. I was just saying, it's minus pi to pi. I could deal with that, right? I've got a pretty strong sense of how to, you know, how can I change a minus pi to pi function to an a to a function, right? Like that really is a simple rescaling. So fine.
Well, can you show that it's even, and then you can show that it's symmetric, so you can just go from 0 to a?
How about this? How do we go from minus pi to 0a? What would the map you want for that to be? We'll assume a is positive. Yeah.
Well, you want minus
Uh-huh.
And then you want pi to map to A.
Okay, so let's say, let's not use f. That's already been used. Bad choice, right? So how about u of t, right?
Yeah.
Oh, no, let's do t of x. My bad. T of x is equal to, well, I wanted to start at 0. So just this, and then then t, rather x, sorry, x times. So if I put x equal to, good grief, I'm sorry guys, I'm having some. This is not complicated. I want.
Sine of pi would be 0.
Here, let me be really stupid. Mx plus b is what I'm looking for. Okay, I want t of minus pi equal to 0. I want t of pi equal to a. This is giving me minus m pi plus b. This is giving me m pi plus b. Can you solve this for m and for b for me?
Yeah.
Right? We can do that. So if I was more awake, I wouldn't have to do the algebra. I'd just write it down, you know? So,
2b equals something.
right? So if I add these equations, I get a is equal to 2b, which is to say that b is a over 2.
To half a.
Yeah, so the b is a over 2. What's my m?
M's going to be equal to 2 pi m over 8 minus a.
A over, I think a is, m is a over 2 pi, I think.
Well, you add them, so you get 2m pi equal to a. And then you divide 2 and pi, so it should be m is equal to a over pi 2 pi. Right?
Did I get it?
A equal to m over 2 pi.
I got, well, the formula I got in the end was t of x is, I'll write it over here again. I got t of x is equal to a over 2 times parentheses 1 plus x over pi. Does that work? Plug in 0, what'd you get?
Plug in negative pi, you get 0.
Oh, excuse me, plug in negative pi, you get 0. Plug in pi, you get a. All right.
Yeah.
Now we're cooking with, what is it called? Yes. Okay. So if I have, so the idea here, I believe, is that you can thieve. All right. So goodness gracious. So I have f in here, right? I can construct g of t, no, g of x equal to f of t of x. If I did this right. X ranges from minus pi to pi. And then that makes f go from, so this is the bridge between worlds. Right here, g is in L2 minus pi to pi. And f, you know, if we just look at f of t, well, and then the f is, again, this is from L2 0a. Now maybe I should do it the other way around too, right? Like, how could I write f? I could write f of t in terms of g of what? Of x of t, right? What would x of t would be the inverse relation. Can you find the inverse relation? Well, I can, if I need to solve t equals to a over 2 times 1 plus x over pi for x. So I get 2t over a minus 1 equals to x over pi, which gives me x is equal to pi times 2t over a minus 1. If I did that right, that should get me that should allow me to construct if a goes from 0 to 1, g goes from what? T ranging from 0 to a, it goes from minus pi to pi. So what these formulas mean is I should be able to take the integral in the complete L2 space and convert it to an integral in the 0 to a space by a change of variables, if I do this right. What did I say at the start of all this? I wasn't going to take too long in the example, but you know, it's like a siren song to me. I can't resist it. It's like actual formulas. We're almost done with this. Famous last words. So integral, all right. So let me start with this thing here. We're talking about the integral from a to 0 to a, right? F of t. Maybe I should start with the other one though. I don't know. I got to start somewhere. I'm going to start here. F of t, e to the minus 2 pi n I t over a dt, right?
Yeah, there's also a 1a outside the integral.
Ah. Yeah, well, okay, I'll leave it, but I'm not sure that matters. But fair enough, fair enough. So if I want to convert this to a corresponding integral in L2 minus pi to pi, how would I do it? I would substitute, you know, t. I would make a t equals to, you know, a over 2, 1 plus x over pi substitution, right? For which dt is, you know, a over 2 pi dx. And so we get 1 over a times a over 2 pi integral. And then, so what happens with this substitution? Well, in the x, 0 goes to minus pi, and a goes to pi. And we have f of what? F of a over 2 times 1 plus x over pi. And then we have e. All right, so what happens with this up here? Do you see what happens? Like, think about plugging this up into here.
The a goes away, the 2 goes away. You get 1, you get pi, and one of the pi's is going to
Pi n,
drop.
pi n t plus, pi n I t.
Pi, yeah, pi nit, I think.
Plus,
Yeah.
And
plus, it would be plus n I x t, right? Because t equals a over 2 times 1 plus x.
yeah, sorry, let me be careful here.
Yeah,
Let me multiply it out. 2 pi nit over a is equal to 2 pi n I over a times a over 2 times 1 plus x over pi.